Well, hello and welcome everyone to today's webinar. Today we're going to be discussing online partial discharge testing, a powerful tool for the reliability manager. My name's Tom Sandri. I work in the Workforce Development Department for Shermco Industries, and I'm going to be your host today. And actually traveling and on the road right now, broadcasting to you live from Baton Rouge, Louisiana. So kind of tucked away in a hotel room, hoping desperately that the maid doesn't come along and knock on the door and disturbs us while we're going through our webinar today. But again, other than a little bit of the comedy relief, please be a little bit patient and tolerant just in the event that the door goes a knocking for me. All right, let's get started. Let's go ahead and take care of some basic housekeeping first. So before we get started, please allow me to address how we interact with one another and participate during these type of webinars. First off, at the conclusion of the webinar, there will be a live questions and answers period where I will read through the various questions that have been posted during the course of the webinar, and I will do my very best to address them all at that time. If, however, we do run out of time and I can't get to everybody's question, when you use the questions function on your control panels, your question will be logged in and registered. So even if I don't get back to it during the course of our webinar, I will have it on file and I will be able to go ahead and respond to you one-on-one via email. So please, as the webinar is going on, if a question does form in your mind, write it down, or better yet, go straight to the questions function, type in your question, and get it logged into the system. Also, everyone who is in attendance will receive a copy of the presentation that we're giving and a link to a recording of this particular session. And finally, excuse me here a second. You will also receive an email in approximately 72 hours after this webinar has concluded. And this email will act as a documentation of your attendance. This email can then be used to earn one continuing technical development or CTD credit with NETA, or one professional development credit that will go towards your PE. Now, one last item. On your control panels, you may see a hand icon. That's kind of the equivalent of raising your hand in a classroom. I'm going to have you use that hand icon right now. If you are able to hear me in the broadcast, please click on your hand icon. Oh, fantastic. Okay, sounds like we are broadcasting and everything is working. All right, feel free to lower your hands at this point, and we're going to get started into the actual presentation. All right, in this session, we will be discussing, obviously, online partial discharge testing. But specifically, the topics that we're going to go into will include predictive maintenance, diagnostic technologies, what is partial discharge detection, types of partial discharge. We'll talk about different sensors, how they operate, and sensor technologies. We'll take a look at different examples of surveys, a switchgear survey, gas insulated system or GIS survey, or transformer surveys. And also, we will talk a little bit about partial discharge limitations. All right, since partial discharge is a form of predictive maintenance, let's talk a little bit about what is predictive maintenance. Now, predictive maintenance techniques are designed to help determine the condition of in-service equipment in order to predict when maintenance should be performed. Now, this approach promises cost savings over routine or time-based preventative maintenance because tasks are performed when warranted. Now, the main promise of predictive maintenance is to allow convenient scheduling of corrective maintenance and to prevent unexpected equipment failures. The key is getting the right information in the right time period. By understanding how assets are aging and knowing which equipment needs maintenance, maintenance work can be better planned. For instance, spare parts, resources of people, etc. And what would have been an unplanned stop, these are transformed into fewer, more focused planned stops, thus increasing plant availability. Other potential advantages include increased equipment lifetime, increased plant safety, fewer accidents with a negative impact on either people or environment, and optimize spare parts handling. So these are all kind of the promises of a predictive maintenance approach to running and operating our plants. Now, partial discharge testing plays a critical role in determining the health of your electrical assets and ensuring maximum uptime. Partial discharge testing provides reliability managers with with the critical information to target maintenance resources to the areas that require attention. Now, as with any diagnostic technology, however, an understanding of how the technology works and implementing a logical approach will become necessary in order to render an effective online program. All right, looking at what exactly is partial discharge, I'm going to go by the IEC 60270 definition. Partial discharge is a localized electrical discharge that only partially bridges the insulation between conductors and which can or cannot occur adjacent to a conductor. Okay, pretty interesting definition there, but let's go a little bit deeper. When the voltage stress exceeds the breakdown strength of a certain section or portion of insulation, a partial discharge begins and continues to deteriorate that insulation. When partial discharge occurs, various physical and chemical changes may happen, which produce emissions that we can detect, localize, and characterize to provide the information needed to prevent insulation failures on medium and high voltage electrical equipment. Partial discharge occurs in solid, liquid, or gaseous insulating mediums. Partial discharge can also occur in the form of corona, surface tracking, or floating electrode, metal-to-metal discharges, causing degradation of the insulation. Now, once partial discharge begins, it always gets worse. Now, the NFPA 70B recommended practices for electrical equipment maintenance has a statement in it that says that insulation breakdown is the #1 cause of electrical failures. So catching insulation breakdown as early as possible, again, leads toward reliability and runtime. Excuse me. My sinuses are just absolutely horrible today, so please forgive me. All right, let's go a little bit more into what is partial discharge. In some materials, the insulating medium is not completely solid or uniform, so there may be air voids. Essentially, there are two sets of resistance, one of the material and one of the air void. The resistance of the material is higher than the air gap, meaning the insulation has a higher dielectric strength than the air pocket or gas void. As a voltage is applied, the voltage stress across the air gap is higher than on the insulation. The walls of the gap are stressed and begin to break down or ionize. Now, eventually, these ions build up and the resistance of the air gap breaks down, and a discharge occurs across the gap. Okay, this can potentially leave semiconductive residue or carbon behind, which is conductive, kind of like a stress crack on the insulation. Now, over time, this will build and can lead to or create a full discharge, as we kind of walk through there in that little animation. All right, let's talk a little bit about partial discharge detection. Online partial discharge testing methods offer the opportunity to discover potential problems under normal operating circumstances. The online approach is a non-invasive, non-destructive, predictive test procedure. These tests can be either periodic scans in order to obtain a quick assessment of your assets and the insulating systems. They can be short-term monitoring over a longer or extended period of time to provide more accurate assessment over changing conditions, or they can be continuous monitoring to analyze assets during day-to-day operations in order to detect deterioration or a raise of alarm or call to action if partial discharge activity reaches certain critical levels for certain devices. Now, detection of partial discharge related faults is based on the principles of determining whether PD activity is at a critical level or not. Low levels of partial discharge activity are often present in assets at levels which may be considered acceptable, non-critical, or unlikely to develop into failures in a short or medium time period. So, understanding of the insulating material becomes very, very important when putting together an online partial discharge testing program. Because again, certain materials, let's take for example, the mica tape that may be used in the windings of a rotating machine or a motor stator. Mica is very, very resilient and a very durable dielectric that can withstand partial discharges for years and years of faithful operation before any damage or threat of failure may occur. Now, in contrast, we might have an insulation like the ethylene propylene rubber used in medium voltage electrical power cables, or the cross-linked polyethylene used in many medium and high voltage cables. This is less resilient to or offers less resistance to the partial discharge. Partial discharge in this type of insulating system may go ahead and go from initial partial discharge to failure in possibly months or a few short years, depending upon the tracking path and so forth through the dielectric. So again, an effective program really requires some level of knowledge of what you are testing and the type of insulation. Okay, in the next slide, let's go into and talk a little bit about partial discharge conditions. Okay, condition 1, partial discharge activity is not present or is at a subcritical level. The results provide assurance that PD-related faults are unlikely to occur or to be developing anytime in the near present. Okay, so this is obviously the best condition to be in. After we do our scans or monitoring, we come back and notify you that you are in condition 1. nothing really significant to report. Okay, condition 2. Partial discharge activity is at a level which indicates that a fault is developing and requires further investigation or monitoring. Now, partial discharge is a symptom, not necessarily the failure mechanism. It's normally a symptom to something else going on. So in a condition 2, hopefully we have caught the partial discharge activity early enough to where the fault is just beginning to develop. But now the nature of the game is to try to find the trigger mechanisms, what's causing it. So here, the investigation or the monitoring might be looking at load cycles. Does the partial discharge seem to kick in when load cycles go up and then dissipate when load cycles go down? Possibly it's triggered by thermal, maybe weather condition and so forth. Heaters inside the switchgear cabinets maybe are at fault and are actually the root cause of the problem. So during very hot, humid days, moisture content builds and we're in a condition 2 partial discharge showing evidence of possible corona or tracking activity. Okay, finally, condition 3. Partial discharge activity is at a level which indicates that a fault is at an advanced stage of development. The fault is likely to cause imminent failure, and the asset may be energized to an extent that is a danger to the personnel. This level of PD activity obviously indicates the need for immediate investigation and/or intervention. All right, let's explore different types of partial discharge. The first one we show here is called the void discharge. This type of discharge is typically caused by manufacturer's defects in solid insulation systems. We see this in cables, bushings, GIS junction insulation. Now, void discharges are highly destructive to insulation. Voids typically continue to grow until a point of failure. If a void partial discharge is discovered, the insulation should be investigated, monitored, and/or replaced. Now, again, replaced, let's take that with a little bit of grain of salt because, again, understanding of the type of insulating system and how quickly it can potentially go to failure is going to be very useful. In the slide, the image, I basically show a motor winding, like for instance, in a stator. And the voids that we see here are delamination or gaps in the mica insulating tape. Now here again, since mica is used as the insulation, we may have partial discharge activity in these voids for a very, very long period of time before they can finally erode and break through the ground wall insulation. Now, if the picture I chose to put up there, let's say, was a cross-sectional image of a crosslink polyethylene cable that had little voids in it, these are going to be much more of a concern if we detect void discharge in this type of insulating system because they will deteriorate, grow at a much more rapid rate by the nature of the dielectric. Okay, the next type is corona discharge. Corona discharge, in short, can be kind of defined as medium and high voltage, where we are seeing discharges to the water molecules in the air or atmospheric discharging taking place. The more proper definition would be corona discharge is one of the 5 distinguished types of partial discharge. For example, breakdowns caused by high voltage, which does not cause a short circuit. Corona discharge is a current flow, usually in the air, from a discharge electrode, which is under high voltage. High voltage is a source of air ionization, which creates plasma around the electrode. It is ionized matter containing electrically charged particles. The resulting ions carry the load to a place of lower potential. The discharge is invisible in the daytime. Typically, it's in the form of ultraviolet radiation, which normally we will not be able to see with the naked eye in the daytime. In evening conditions or blackout conditions, possibly we might be able to detect some of the corona as a blue-violet afterglow that we might see radiating from the tips of bushings in a substation yard. Now, the development of ultraviolet radiation detectors or corona cameras have become very, very useful tools. And we'll talk more about them when we talk about sensors. But prior to the ultraviolet radiation detectors or corona cameras, one of the methods of determining corona coming off of substation equipment would have been the use of ultrasonic acoustic air-based detectors, which again, we'll talk about in a little bit. In the acoustic, many of you may have already experienced like on a hot, humid day, you're near a high voltage substation and you hear the hissing, crackling, and popping sound coming off the bushings. Again, if those discharges are into the atmosphere, into the water molecules in the air, they are relatively harmless in nature. Surface discharges. Discharges along the surface of insulation can be very destructive. This type of discharge is also known as surface tracking. Now, usually caused by contamination or weathering of the insulator surface. It is different from corona because it tends to want to track to ground or fine metallic ground. Corona discharges are discharges to the water molecules in the air and again are relatively harmless. Now, corona, however, can transition into surface discharges if the surfaces of the insulation, suffers or gets worse through contamination or semiconductive residues beginning to form. Okay. So again, areas of surface tracking could be caused by humidity, contamination getting up onto the red board within switchgear or along the porcelain bushings in a substation yard. Normally, the counteraction to this would be, again, inside the switchgear equipment, ensuring that the heaters are operating. We're keeping moisture and humidity levels under control so that contaminations do not build up on the sidewalls or on the insulators and so forth. In the substation yards, corona transition into surface tracking may indicate that it's time to bring the station down, do a power washing and re-waxing and conditioning of the porcelain, excuse me, went totally mind dead here, bushings. Yes, that was the term I was looking for. Okay, the next is a floating discharge. Floating discharge occurs when an exposed load-carrying conductor is exposed to another conductive surface of different potential, not bonded or connected to that conductor. The types of floating discharge may include metal to insulation or metal to metal discharges. This type of discharge is commonly caused by installation or assembly errors, poor positioning and clearances of conductive elements, and or poor bonding techniques. Floating discharge is a very common type of partial discharge. Excuse me. So in the image we see here, we see basically a phase-to-phase discharging taking place due to inadequate clearances. And I believe this photo is of some cables landing into the pecker head or cabling compartment on a motor. Okay, and the fifth type of partial discharge we refer to as particle discharge. This occurs in gas insulated systems or SF6 or oil insulated systems like oil transformers. Particle discharges are caused when conductive particles and impurities are left inside the insulating system. The activity occurs when partial discharge jumps from conductive particle to conductive particle. Now, the corrective action typically is purifying of the SF6 gas or purifying of the oil. All right, let's talk a little bit about sensor technology. Now, in the image here, I kind of refer to sensor technology and the partial discharge receiver or partial discharge detection test set as kind of being a radio, and the partial discharge sensors as being different antennas designed to pick up different frequency bands. Again, in the online world of partial discharge, the energy is emitted in the form of different frequency bands and electromagnetic waves. So depending upon where the partial discharge is or the type of partial discharge, the various sensors, in a very simple analogy, can be referred to as different antennas picking up the events. And the partial discharge test set can be just, very simplistically referred to as sort of like the radio picking up these different frequency bands. Here I kind of show a little bit more proper example. Here we show a piece of test and measurement equipment. This would be the partial discharge receiver, and we see various antennas, if you will, or sensors. Each of these sensors operate at various bandwidths. Let's start with the UHF sensor, or the ultra high frequency sensor. Now, ultra high frequency or UHF sensors, depending upon the manufacturer, will typically operate in a bandwidth of 300 megahertz out to about 1500 megahertz. Again, from manufacturer to manufacturer, there might be some slight variation to that overall bandwidth, but somewhere in the realm of radio frequencies and microwave frequency ranges. Every time a partial discharge event occurs, electromagnetic waves are transmitted from the site of the defect. This emission may also be called RFI, radio frequency interference, or EMI, electromagnetic interference. The partial discharge emission is a broadband electromagnetic emission which can range from the upper radio frequency range up and into the microwave range. Again, typical bandwidths are around 300 megahertz out to about 1500 megahertz, depending upon manufacturer of the sensor. Now, all types of partial discharge will produce electromagnetic emissions in the UHF range. In most cases, the UHF emission is detectable with the UHF sensor. The UHF pulses are going to be emitted from the site of the PD defect and will spread in all directions through the air and through most materials. However, the signal cannot travel through metal. Metal enclosures will shield the UHF emission. The signal can escape, however, through tiny cracks or gaskets and or seals, and then respread out into the air. The pulse will occur at or near the positive or the negative peak amplitude of the AC sine wave. Thus, the ultra-high frequency pulses will occur at intervals roughly equal to 1/2 the AC cycle time. So for 60 hertz, that would be 1/60th or 16.66 milliseconds in a cycle. So the UHF pulses would potentially occur at half these values or at 8.33 milliseconds. To prove that the UHF that we're picking up could be from a partial discharge activity, we can show that there is a 180-degree separation, 8.33 milliseconds, between the UHF pulses that we're picking up at the sensor feeding into the partial discharge receiver. This is a function of time resolved or phase resolved measurements. The phase resolved measurements excuse me, are made in real time and serve as a basis for very quick PD detection assessment in the field. Now, In some cases, such as inside of a power transformer, the UHF emission may be completely shielded by the sealed metal enclosure of the transformer. Well, fortunately, the UHF signal will also induce a high-frequency current pulse onto the grounds of the apparatus. The high-frequency current pulse will be detectable with a special high-frequency CT, referred to as an HFCT. And that leads us into the next sensor, the HFCT sensor. High-frequency current transformers or transducers typically operate in a bandwidth somewhere around 500 kilohertz out to about 50 megahertz. Again, it may vary from manufacturer to manufacturer, but that's kind of the general range. When partial discharge occurs, there are small current pulses that are induced onto the ground shield or case ground. These pulses will travel dozens of yards or meters along the ground grid in the form of high frequency current pulses in the frequency range, as I mentioned, about 500 kilohertz out to about 50 megahertz, with usually a center frequency in and around the 10 megahertz realm. High frequency current transformers are a reliable method to measure these high frequency PD pulses. These pulses spread out onto the ground grid like ripples in water. They are especially useful for quickly testing for internal PD in a large area, such as if PD is present in a power transformer, or if PD is present in a long section of cable, or even if PD is detected or possibly sensed in an entire substation. The high-frequency CT sensor has a split core, and so it's simply clamped around the low-resistance grounding lead. HFCT sensors have a distinct advantage of being able to detect partial discharge signals on cables from long distances up to several hundred yards or several kilometers. Now, the only limitation is going to be the type of shield and how good that shield acts as a conductor as to what is the actual range and how far away you will be able to pick up PD transients. Now, this means of multiple, excuse me, this means multiple PD signals and noise can be potentially picked up and detected on these CTs. So when doing a live online assessment, having the ability to adjust the bandwidth becomes very helpful for determining if we're looking at real partial discharge or if we're looking at noise being picked up. So again, that's an attribute of the receiver. A lot of times the CT will have a wide bandwidth, but the receiver will allow us to select certain noise filtering in order to determine if we're just picking up random noise from the environment or if we're actually picking up valid partial discharge emissions. Also, the high frequency CT lends itself to the ability of helping us to locate the location of partial discharge, for instance, in cables. Here we show an example in this slide where we have a cable section. The CT is clamped around the concentric neutral of the cable. And if a PD, whoops, let me bounce back there. If a PD event occurs, for instance, where the little star is in my picture, a current pulse is going to launch in two directions. The pulse that initially launches toward the receiver passes through the CT at time period number 1, and we clock in that pulse. Meanwhile, the current pulse that launched off the back end of the partial discharge location reaches the end of the cable or an area of impedance change, reflects off of that point, and travels toward the CT, passing it at time period number 2. Now, if we know the velocity of propagation, how fast the pulses are traveling on that particular type of cable media, and we measure the time differential between the first and second received pulse, we can actually calculate the distance or the location to where the partial discharge events are occurring. All right, let's move into airborne ultrasonic sensors. Airborne ultrasonic sensors include things called parabolic dishes, ultrasonic extension wands, and these devices typically operate in a frequency band of about 20 kilohertz out to about 80 kilohertz, and will normally offer a center frequency somewhere in the area of about 40 kilohertz. Again, that may vary from manufacturer to manufacturer. Each time a partial discharge event occurs, an ultrasonic emission is transmitted from the site of the defect. The emissions are typically in that ultrasonic range of about 20 kilohertz and up into as high as possibly even 300 kilohertz, and may also extend into possibly some of the lower frequencies into the more audible range. If an insulation defect is close to the surface, then the ultrasonic signal will spread out and become airborne. The airborne ultrasonic signal may be detected by one or more of the three airborne style sensors. Now, an extension wand can be used. Now, the extension wand, if you look to like the right-hand side of the photograph in this slide, the gentleman is using the extension wand. This can be used to help reach into hard-to-reach areas, seams in cabinets and enclosures, and then amplify any of the airborne acoustic emissions that are taking place if PD is present. Now, another type is the parabolic dish, which is used to extend the distance or the range of the ultrasonic microphone. Now, it's very common you see these parabolic dishes used in the outside plant area. For instance, you may see a technician in a substation pointing these up toward the bushings on the breakers and on the transformers. Again, this is a listening-based technique. The ultrasonic signals in these frequency bands that you're going to pick up, the gentleman with the headphones are listening, and what they're listening for is the traditional hissing, popping, or crackling type sound associated with ultrasonic or airborne partial discharge. Let's talk a little bit about acoustic emission sensors or contact sensors. These sensors, again, operate in very similar frequency bands as the airborne acoustic sensors, again, in the 20 kilohertz out to about maybe the 300 kilohertz realm. The acoustic contact probe is ideal for detecting and localizing partial discharge in fluid dielectrics such as oil or SF6 gas compartments. This is sometimes called in-tank testing. Each time a partial discharge event occurs, an ultrasonic emission is produced at the site of the defect. If the defect is inside a sealed compartment, such as a transformer or SF6 compartment, the signal will usually not become airborne. In essence, it may need to travel through the media or through the oil. Now, fluid or solid dielectrics such as oil, SF6, and resins will permit ultrasonic PD signals up to around 300 kilohertz. However, air cannot permit ultrasonic signals higher than roughly 80 to 100 kilohertz. To use the the AE or ultrasonic contact probe, it is a best practice to apply a high vacuum silicone gel to the contact probe to bridge the air gap between the exterior of the tank that we're placing it on and the contact sensor. This gel will act as a conduit and will help conduct the PD signal from the exterior of the tank onto the ceramic head of the acoustic contact sensor, giving us better amplification and clarity of sound when we're probing along and looking for these ultrasonic events. The image here basically shows an oil breaker in a yard, and we see that there is a contact sensor placed on each of the sections of the breaker. This particular one we see goes down into a little module, and these are more permanently installed and are continually sensing. Again, these sensors can be either temporarily installed for long periods of time, they can be permanently installed for continuous monitoring, or they can be detachable, carried with a PD receiver, and just probed along for scheduled surveys. All right, the next sensor we're going to take a look at is called the TEV sensor. And TEV stands for Transient Earth Voltage. These sensors typically operate in a bandwidth of about 300 megahertz out to about 100 megahertz. Partial discharges in medium voltage power equipment will produce induced radio frequency signals which are sustained and can be detected at the surface of medium voltage enclosures such as metal clad switchgear, manholes, and metal enclosures. Transient earth voltage or TEV signals spread out quickly on the ground plane. For this reason, it is very difficult to locate the actual origin of a transient earth voltage signal. Partial discharge from overhead can also induce a TEV signal on an entire line of switchgear. I guess to kind of break it down, the TEV or transient earth voltage is created from the emission of the partial discharge. The emission of the partial discharge is going to create electromagnetic waves which are going to propagate, and when they hit the metal cladding of the switchgear or the enclosures, they're going to impinge, I guess is the proper term, impinge a voltage onto the metal cladding. Now this transient earth voltage can be down in the millivolts or to just a few volt level. The danger or the problem is there are lots of sources of electromagnetic energy in typical switchgear rooms. Electromagnetic energy can be produced by variable frequency drives. They can be produced by battery chargers, fluorescent lighting systems, large motors. So when you're using this technology and you're probing, there may be areas where over a large surface area, you're picking up rather large transient earth voltages. You should look around and use some situational awareness in those areas where you're picking up high levels, but it's spanning a very large area, like maybe multiple cubicle bays. Look for external sources of electromagnetic waves that may be creating or causing. Now, by using multiple TEV sensors, if the partial discharge is coming from inside the cabinet, it's going to be in a very concentrated area. So using multiple TEV sensors, we can probe along, and basically as we move in various directions, the TEV signal gets stronger or weaker, helping us to triangulate in onto the area behind the cabinet where the PD events are occurring. But again, be careful of the TEVs because electromagnetic waves can easily be produced by external devices such as fluorescent lighting systems, LEDs, battery chargers, heaters mounted to the side walls, etc. So many times we'll use like a TEV signal, but then we'll also use the UHF or the high frequency CT or even the ultrasonic airborne sensors as backup techniques to kind of say, yes, what we're hunting here is in fact, actual real partial discharge, whether it's surface tracking, floating discharge, or corona. All right, let's talk about the UV radiation or the corona cameras. Now, the corona cameras or the UV radiation detectors actually measure in the electromagnetic spectrum, and typically will have a range of like 200 to 405 nanometers. Now, when you're using this type of tool, there are other sources of UV radiation, solar, the sun, sunspots. So typically when you're using this type of cameras, we see the gentleman in the photograph, uh, he has the lens of the camera pointing up into the substation. He's looking through the viewfinder. What he will be seeing is little flashes of white light, the UV light. Now, if he's pointing that camera into, let's say, just the sky, but not a focused target, he may be getting many little random little bursts of light. These are little sun flares that he's picking up, little ultraviolet radiation. Now, if he's pointing it toward, let's say, a bushing, and at the tip of the bushing, he's finding very repetitive, continuous little bursts of white light, what he's probably witnessing is the ultraviolet radiation occurring from the corona discharges into the atmosphere. Now, let's say he's also viewing that same bushing and he sees a stream of flashing light, little bursts of white light, repetitive, and following the same path. What he is probably visualizing is surface tracking going down the bushing. So the camera is very, very useful and allows us to visually see exactly where the surface tracking or the corona discharges are taking place. Now, we can also use the parabolic dish pointed at the same location that the camera is picking up these activities, and we should be able to get the audible sound of the crackling, hissing, and popping of corona or tracking. All right, the final detector that we're going to talk about is the high voltage capacitive coupler. Now, this is used for online testing, but as we see in the photograph, it requires an outage because this detector is actually installed and left permanently installed in the gear. Now, the photograph I show here shows these couplers installed in the cable landing compartment of a large motor. And the coupler, the bus coupler, the green coupler that we show here, is connected between the conductor and the ground plane. Coming off the low side, there is coaxial cable that feeds and goes out of the enclosure, and the node that is used can either be a non-sophisticated node that, for instance, here just has B and C connectors, and periodically I can bring a scanning device, a PD receiver, plug it in, scan any activity that's being picked up by these bus couplers, and do an online scan of the asset. Now, in a more sophisticated, it could be a smart node, and it could actually have a measurement circuit and a PD detector built into the node itself. And this could be continuous online monitoring. So again, depending upon what level of sophistication you want to get into, it could either, again, be an unsophisticated node where a technician comes out on some scheduled basis and runs a scan to trend the condition of the insulation or any PD activity, or it can be a smart node and could actually be doing the measurements and text messaging you or emailing you if thresholds are being exceeded and a call to action is being required. All right, let's move on to some samples of surveys. Here I show a sampling of switchgear survey, and I'm showing kind of the rear panel of the switchgear lineup, because this is typically where the medium voltage bus or the high voltage bus is running. This is where possibly where the circuit breakers are racked in and engaging or seating onto the bus. Be most advantageous to pick up at the rear panel of the cabinets. This also could be where the incoming or outgoing cable landing compartments are located. And I showed multiple sensors here. One would be to make a pass-through using the transient earth voltage sensor. And typically we would place the sensor toward the top of the cabinet panel, midway in the panel, and toward the bottom of the panel, and we would document the different levels. Now again, if we're getting very high TEVs, but they seem to be over many panels, I may look for external sources of electromagnetic waves. I may look for space heaters in the area. I may look for variable frequency drives. I may look for fluorescent lighting fixtures directly overhead. That would basically explain why I'm picking up such a wide area of TEV. Now, as a backup to the TEV reading, where I show the little vents, here the ultra-high frequencies, although blocked by the metal panel, can escape through these vents. Now I can pick up the ultra-high frequency, and if there is partial discharge occurring behind these panels, the TEV might give me one clue, the ultra-high frequency sensor, and viewing it on the receiver, seeing these current pulses or these bursts occurring 180 degrees out of phase from one another can give me assurance that I'm actually looking at actual PD occurring behind the panel. I also show where the the acoustic emission contact sensor, can be used and placed on these cabinets at various locations. This would give me the ability, like a stethoscope, to audibly able to listen inside the cabinet, and what I'd be looking for is that crackling, hissing, and popping sound. So by using all of these technologies together, I can get reasonable confirmation and a good feeling that I am tracking real partial discharge and not just some random false hit indication. Next, I'm going to show an example of a survey on GIS bus system. Notice here again, we use the ultra high frequency sensors, but I don't use them along the bus. I strategically use them at seals and gaps where the ultra high frequencies can escape from all the metal. So strategically using the UHF sensors in these locations can give me indication, or at least help me sectionalize the sections of the bus that may have partial discharge or particle discharge activity occurring in it. I can also use the contact sensors and listen anywhere along the metal cladding or anywhere along the metal enclosures. The next I kind of show surveying of a yard transformer. Here again, the UHF sensors may be used at the drain valve. I could potentially use them up where the bushings, the seals are. Again, anywhere where possibly the ultra high frequencies can escape the metal and make their way back out airborne. I also show the use of the high frequency CT, where the use of it here in the yard, I might go from asset to asset, breaker to breaker, transformer to transformer, and periodically take measurements with the high frequency CT along the ground grid. And let's say I get over to this particular transformer and I get very high peaked up readings above the baseline that I'm establishing on all the other assets in the yard. That helps me give me an indication that there is possible PD happening inside the tank. Now I can use the contact sensor strategically placed along the tank. And again, the sensors that give me the strongest indications or strongest readings will help position where the PD is occurring within the tank of the transformer. So again, we use multiple sensors, strategically placing them. You'll notice that the transient earth voltage sensor is not used in this situation because the electromagnetic wave needs to propagate through air passage, and in an oil-filled transformer tank, we really would not pick up any type of TEB signal. And finally, surveying an entire switchyard or substation. I could be using the UV radiation camera or the corona camera and photographing any type of ultraviolet discharging activity on the bushings, switches, etc. in the yard. I could be using the airborne parabolic dish and listening for the tracking sounds as I move up and down the bushings and so forth. I could be using the high frequency CT to help isolate which of the assets is exhibiting signs of partial discharges. So again, in the yard, the ultraviolet or corona cameras and the airborne ultrasonic receivers become very, very useful. Also the UHF receivers. Again, if it's an SF6 breaker, as long as I can get to the seals, the gasket areas where the ultra high frequency signals have a chance of escaping, I could potentially use this sensing device to determine if I am in fact tracking or picking up partial discharge. All right. Now let's go through analysis and recommendations. Many factors must be considered when assessing insulation quality, such as the age, visual appearance, the environmental conditions, partial discharge magnitude, and partial discharge rate of change, partial discharge signature, and comparison of this data to similar insulation installations. Collectively, these factors will help provide useful insight to the present condition of the insulation and its projected lifetime or projection to failures. Again, knowledge of the type of insulation and how slow or how quickly it may erode under partial discharge, events such as void discharge, tracking discharges, and or floating discharges, metal to metal, metal to insulation. Knowledge of the insulation of the dielectric material obviously helps in making these predictions and trending as to when we need to take immediate action. Partial discharge testing is utilized to determine insulation condition and as an early warning of impeding failure. Uh, those of you that do infrared studies, an infrared or thermography study helps you determine bad conductive connections, loose hardware by showing IR drops. And this is also a form of predictive maintenance. Partial discharge is sort of like the peanut butter to the jelly of thermography studies. One is showing you mechanical damages or mechanical failures occurring. The partial discharge shows you trending or events that are happening in the insulation. So again, thermographers armed with partial discharge sensing and detecting equipment is kind of that 1-2 punch of the reliability management, predictive management world. Here we show a sample of some UHF patterns. And remember when we were saying about 180 degrees apart, they would typically occur during the positive and negative peaks. So here we see the data captured, the measurements basically being translated into little dots of different amplitude variations. But notice the pattern shows us two bursts 180 degrees apart from one another. This can be distinguished as actual partial discharge activity occurring and not random noise being picked up by the antenna. Here we show kind of a repetitive pattern, almost looking kind of like a picket fence. It's sort of a repetition, evenly spaced pattern. This is very commonly picked up when we get near rotating machines. And again, as they're rotating and so forth, there is a repetitive cycle pattern that we may pick up with the UHF sensor. And finally, we see the pattern for just excessive random UHF noise that we're picking up. This may be because we're very, very close to lighting fixtures, lighting balance, reactors, heaters, battery chargers that are just producing a large array of electromagnetic interference in the area. Okay, and in conclusion, let's talk a little bit about limitations. Okay, Although partial discharge, online partial discharge testing is a wonderful tool, again, I caution it does take knowledge and experience, understanding of how the sensors and the technology works, and an understanding and knowledge of the type of insulation that we're studying. There are situations where even with online PD studies, a fault occurs. Now, this could be caused by human error accidents. Somebody is working on or near, causes a short circuit event, a crane accidentally comes in contact, with a bushing, or, again, a human error factor. It could be caused where we're tracking the partial discharge events, but a large lightning or transient surge has come along and was just the final punch to drive it into full discharge. Mechanical failures. Insulation damage due to rodents or other pests getting in there and, in essence, messing up our trends by eating through the insulation in a more rapid fashion. The defect is at very an advanced stage. The defect may already be conducting through a carbon path. And this is kind of interesting because as the tracking path matures, like sort of on this bus picture, as this path matures, there's less discharging, and since you already have a semiconductive highway being established, we just get increased leakage current. So in a very advanced stage of partial discharge, I may lose detection of the electromagnetic signals and all being produced because I'm no longer getting the discharges. Instead, I'm getting very high leakage current going along those semiconductive tracking lines. The partial discharge source may be inactive at certain times. This is one of the things with online partial discharge testing. If you embark upon online partial discharge testing and you're only going to do this once and never repeat it, there are other more cost-effective ways to spend your maintenance dollars. Partial discharge testing online is a snapshot in a specific moment of time. What were the load conditions? What were the environmental conditions? Was the trigger mechanism of partial discharge present when you took the picture? So if you're going to embark upon this type of program, I would highly recommend, possibly for the first year, if you're new to this, have a scan performed maybe once a quarter. That gives the ability, one, to go ahead and look at the asset under different operating conditions, different seasonal conditions, hopefully temperature variations, load variations, etc. It also helps to gather data points as to, is what we're picking up remaining stable, non-change over the time periods? Is it fluctuating, changing? It helps us make decisions of what to do next. Okay, cross-linked polyethylene cable may contain water trees. For the most part of the life, when the water is present in the tree, we don't get partial discharge activity. However, if the moisture begins to evaporate out, leaving voids, partial discharge activity can all of a sudden materialize. And then if the conduit takes in a lot of water, ingress gets back in and floods the tree, the PD goes into remission and we don't see it anymore. Here's where offline techniques such as tan delta testing and everything on the cable can help indicate contamination building up in the dielectric versus electrical treeing or voids that may be producing partial discharge. Okay, we actually went just slightly over our 1 hour. My apologies, but a lot of material to cover. We're now going to go ahead and open up the session for questions and answers. Okay, so let me go to the questions board. Looks like I do have some questions that have popped up. Let's see. What bandwidth of the UV sensor is normally used? Any filters used? Okay, definitely, Brian. Filters are definitely always use. The filter typically is not inside the sensor though. The filter is normally inside the receiver or inside the partial discharge detection test set. So the receiver is kind of a broadband measuring over a certain bandwidth, like I covered as I went through the different sensor types. And then the receiver kind of processes and will set narrower or wider filters in order to filter out noise and so forth. And oops, oh my goodness, my apologies. You're actually referring to the ultraviolet sensor or the corona camera. Again, these are actually not frequencies, but wavelengths. Since we're dealing with ultraviolet light, they're measured in wavelengths. And if I'm not mistaken, I believe the range is somewhere around the 200 nanometer up to around the 400 nanometer. And in the corona cameras that I've used personally in my career, there was no filtering. Really, what you were doing to see if the difference between sunbursts or sun flares versus actual corona or tracking was if the little bursts were very random in nature, non-repetitive, just kind of willy-nilly flying on the camera screen. Normally those were the sun flares. If you were pointing it at a specific target and you were getting consistent, repetitive, on that bushing at a very precise location, that was your assurance that you were actually looking at the actual corona or the tracking. All right, moving on. Is there any correlation that can be made that a PD activity increases, maybe hits a peak, and then trends down? Would this be identified with other offline testing and inspections? Oh, that's an awesome question, Kevin. Yes, let's say we were trending online and we were mapping the life of partial discharge in this particular apparatus. At some point, the gap or the void would grow to a point where partial discharge is now detectable and we would start to be able to see it. As the void grows through the discharging activity, we would start to see that the intensity or the PD levels start to go up, up, up. And actually the bursts per cycle begins to increase as the PD advances. But now let's go back to the matured point where it's really at the verge of possibly going to failure. Now what may happen is we have an established tree with carbon deposits or tracking lines. So instead of having discharging activity, discharge in the void doesn't occur because we already have a semiconductive track line, and we just have increased tracking current or leakage current going through the insulator. So on the final stages of PD, if we were actually trending this over an extended time period, we would actually see a diminishing of PD right before failure. Hope that answered your question, Kevin. What method of online testing would you use on underground or overhead medium voltage cables? Well, definitely the problem with underground cables or even overhead, if they're shielded cables, is the partial discharge typically is going to be happening within the dielectric material and therefore is not going to go airborne. So ultrasonic or airborne sensors normally are not going to provide us much help or guidance. In the direct buried, if it's at least going through duct bank, and let's say that there are splices in the duct bank, there are ultra high frequency sensors that you can wave over the splices if you can get access to them and detect if there's any ultra high frequency activity taking place within the splice. Now, obviously in a direct buried, other than excavating, there's no way to get access to the cable. So here the high frequency CT and placing the high frequency CT where the cable is exposed, typically on the landing areas, we would put the CT around the concentric or the shield, and the current pulses caused by the transient waves at the shooting out of the partial discharge event, these can propagate several kilometers. Again, the success though is going to be on the condition of the shield or the concentric and how well it can carry those signals over a distance. But the high frequency CT would be best used on the cabling. Let's see, what is the best way to detect PD in electrical machines and to isolate the regions where PD occurs? In electrical machines, such as rotating machines, this is interesting. Online is actually one of the superior methods of trending PD and rotating machines because you have other dynamics taking place like vibration, movement, thermal dynamics, and you will actually uncover more possibilities of degradation in an online than in an offline experience. Here, investing in those bus couplers or those capacitive couplers and installing them into the cable landing compartment of the machinery, the generator or the motor, would probably bear the best as far as when you capture these patterns, when you're going through your pattern recognition, you can actually help determine, is the PD occurring maybe due to delamination at the conductor to insulation interface? Is the partial discharge happening within the core or the bulk of the insulation? Or is the partial discharge occurring at the surface or at the end winding based upon the shape of the patterns? So the capacitive couplers I showed a few slides back would actually be the optimum approach to trending and looking for partial discharge activity in your machines or rotating equipment. Let me take a look here if there's any more questions. What about ribbon shield cables and possible attenuation? Bill, that is a definite problem. Ribbon cables, particularly if there's any moisture that gets under the jacket, they start to corrode, they become huge attenuators. Now, the only benefit you have is if it's in an if you're working in an industrial environment, normally your EPR ribbon-based cables will probably be of relatively short lengths, maybe only tens of feet or a few hundred feet. So unless the shields are in very horrific condition, normally the signals will still carry and the technology is still viable to you, simply because in an industrial situation, the cable lengths are not all that terribly long. Now, let's say that you were a utility outside plant, and for whatever reason you were using shielded cable over thousands of feet. Unfortunately, probably there will be much attenuation in order for the online PD of the cable assessment to be really viable to you. Let's see. Is there a correlation between cable length and PD testing or tan delta testing while testing cable after installation? Okay. In the world of tan delta testing, let's start with that. This is just making a bulk assessment of the condition of your cable. And particularly tan delta is very good for determining if there is contamination in the dielectric. But again, it's looking at the bulk. Cable length, the only way cable length would be a factor is on the offline, how it affects the power supply. If there's too much cable length and too much capacitive loading, you may have difficulty with your power supply and getting up to the appropriate test voltage. But generally speaking, length does not really cause an issue in tan delta measurements, other than possible effect on your power supply and the ability to energize the circuit. Now, partial discharge testing, length could be a problem in the cable because, again, that little transient, which is, you know, very, very low in signal level to begin with, has to travel along the shield. So how far can it travel? At what magnitude must it originate at and still have enough energy to get to my receiver? So definitely length becomes a bit of an issue when dealing with the offline partial discharge testing. And again, a little bit of pre-testing and you know, trying to determine the condition of your shields would definitely help identify whether you are a candidate for PD testing on your cables or not. Let's see. Have you performed PD tests on medium voltage with ethylene propylene cabling rubbers? Absolutely, Jose. We've done that numerous times. Again, in an industrial environment, a lot of times working to our benefits are the ribbon cables are still in decent shape and the cable runs are relatively short, allowing this technology to work well for us. Let's see. And finally, because we're about 15 minutes over schedule, but I have one last question on the board. Is your PD monitoring equipment, okay, is your PD monitoring equipment had a urgent warning alarm signs that show emergency attention needed? Now, the equipment that Shermco typically uses are not the permanently attached long-term monitoring type equipment. Most times our technician goes out there maybe on a quarterly basis to a particular client and runs a survey on their equipment. However, in answer to your question, yes, some of the equipment that's out there on the marketplace that is designed for kind of permanent installation and continuous monitoring, these things can be very sophisticated. You could actually put thresholds, warning, alarm, and when the PD activities is sensed to these levels, some of them are so sophisticated they'll actually send the person in charge, if it's the reliability manager, whoever it is, will actually send them an email or send them a text message saying warning level has been detected. And a lot of times it'll even report back which sensor is reporting that condition. So yes, it can be very, very sophisticated. And I think that was all the questions that were posted. I really want to thank everybody for taking the time out of your afternoon to come and participate in our seminar. I hope this was of an advantage for you. I hope it was of value to you and you got something out of it. Again, there will be a recorded version that you should see somewhere within the next 72 hours hit your email. And at this time, the webinar is concluded. Please feel to log off at your leisure. I may hang out for just a few more moments just to see if any last minute questions come rolling in, but please feel free to log off at your leisure. The webinar is concluded. And please watch your emails for our up and coming webinar for next month. Again, it's going to be at the end of the month. And I apologize, I'm on the road in a hotel. I don't have my schedules out in front of me, so I can't even tell you what the topic is going to be. But trust me, it's going to be very exciting and you're going to want to be there. All right, everybody. Thank you so much for your attendance. Hey, thank you, Shane. I'm glad you enjoyed the session. Continuing education credits. Yes, when you get your email confirming your attendance, you'll need to go ahead and submit that email to NITA. I think possibly Laura McDonald might be a good contact there at NITA, and she can issue you your continuing education credit for this session. I believe that's how it works. Thank you, Matthew. I'm glad you appreciated and enjoyed the session. Well, all right, y'all. I'm going to go ahead and sign off and close the session for all of us. And I think I'm going to go grab me a little bit of late lunch. Take care, everybody, and thanks again for your participation.